we present online learning of a memory for learning rates. We ask ourselves the following question. When learning to execute task 1, which involves learning a mapping from X to Y, what can we learn that helps us learn task 2 faster? In this work, we are looking at learning to learn approaches. But as opposed to prior work within this field, we are proposing a meta-learning approach that can perform learning to learn while learning. On a high level, our approach can be summarized as follows. While learning to perform task 1, we are also learning a meta-learner age. Age can then be transferred to the learning process for task 2, which continues to update age, and so on. The representation of the meta-learner that we consider here is as follows. Age maps observed gradients to parameter updates. This means that without any meta-learning, the optimization process is simple gradient descent, where age performs a linear scaling of the observed gradient. With meta-learning, age performs a coordinate-wise linear scaling of the gradient, where the scaling factors are defined by a function eta that takes as input the observed gradient and is parameterized by phi. In essence, eta predicts a coordinate-wise learning rate. Because of this, we call eta the memory of learning rates. We evaluate our meta-learning algorithm on several problems, including the learning of the inverse dynamics of a 7-degree of freedom manipulator. We use a densely connected neural network with 3 hidden layers to represent the model of the dynamics. The meta-learning is learned via locally weighted regression, involving 100 local models. Our algorithm is fast enough to perform learning at 100 Hz. This is a sneak peek of our results on learning the inverse dynamics for the first task in a sequence of 3 lifting tasks. Here we learn the dynamics online. You see how the error in the dynamics model is reduced over the course of the movement as a function of time. In blue, the convergence of simple stochastic gradient descent is shown. In orange, you see the convergence of the same optimizer with meta-learning active. As you can see, already for the first learning task, convergence speed is increased by a lot. When transferring the meta-learner age to the next lifting task, the new learning problem converges even faster. If you have questions, please find us at our poster.